In this video, we'll talk about constant coefficient systems with complex eigenvalues, how we can approach the complex eigenvalue version of this problem. Let us try to solve our system, x prime equals ax, by looking for the eigenvalues of a like we did before, but we get complex eigenvalues. What happens then? Well, if we hit a complex eigenvalue, we also know that the corresponding eigenvector will also be complex. But even with that, we know that we do still get a solution of the form x of t is v times e to the lambda t, where now v and lambda are both complex valued. Which is good, but if we're trying to use this to model a physical situation, complex valued solutions are not really helpful. If this is like the amount of salt in the tank or population of a species, it being complex doesn't really make any sense. So we want to convert these complex solutions into real valued solutions. And thankfully, we already have a trick to know how to do this, and our same trick from second order equations works in this case as well. And that trick is Euler's formula. Euler's formula, like from before, says that e to the ix is cosine of x plus I sine of x for any x. And we can use that to convert our complex solutions into real solutions because we also have the same result from before, that if I can split my solution into a real and imaginary part, then separately the real part and the imaginary part are both solutions to the original equation, assuming that our coefficient makes a real value, which we're going to be doing in this case. So the idea is more or less the same as before. We take our solution that we found as v times e to the lambda t, where v and lambda are both complex, and we want to split this into real and imaginary parts. Now, I have to be careful with this as they're both going to be vector-valued solutions here. So I'm going to want to actually write out what is the vector and write out what e to the lambda t is. It's going to be something like some exponential term in front, and then a cosine of t plus I sine t type of stuff. And I'm going to distribute everything through before I can split into real and imaginary parts and separate things out. So multiply everything through first, and then split into real and imaginary parts. That'll give us our two solutions, and since they will be linearly independent, they can sort of fill in for the fact that I had two conjugate eigenvalues and corresponding eigenvectors for this problem. Let's see what it looks like in terms of an example here. So I want to find a real value general solution to the system x prime is 0 minus 1, 2, 2 times x. So let's first hunt for eigenvalues and eigenvectors. So eigenvalues first. So a minus lambda I is the matrix 0 minus lambda minus 1, 2, 2 minus lambda. I can find its determinant, which is negative lambda times 2 minus lambda plus 2. So I will see lambda squared minus 2 lambda plus 2. That doesn't factor, so it's quadratic formula. That will tell me that lambda is 2 plus or minus the square root of 4 minus 4 times 2 all over 2, which is 1 plus or minus I. Now I can just pick one of these because I know that the eigenvector for 1 minus I will be the conjugate of the vector for 1 plus I. So just take 1 plus I and find the eigenvectors. If I do 1 plus I, that means a minus 1 plus I times I is negative lambda, so negative 1 minus I, negative 1, 2 minus 1 plus lambda is 1 minus I. Now to check if these two equations are redundant, I'm going to multiply the top equation by 1 minus I. So then I will see here a negative 1 minus I times a 1 minus I, negative 1 times a 1 minus I, 2 and 1 minus I. If I expand out this over here, I will see negative 1 minus I plus I minus 1. So it's negative 2, which means the matrix becomes negative 2, negative 1 minus I, 2, 1 minus I. So these are the same equation. It's a redundant equation here, so we're okay. And now I want this times a vector v to equal 0 to find the eigenvector. And the second row here tells me that 2v1 plus 1 minus I v2 must equal 0, which I can make happen by setting v1 equal to 1 minus I and v2 equal to negative 2, because that makes the whole thing go to 0. So that means what I have is I have eigenvalue 1 plus I with corresponding eigenvector 1 minus I and 2, negative 2. So my solution then will be 1 minus I minus 2 times e to the 1 plus I times t, which now I want to split into real and imaginary parts to write my general solution. So I see 1 minus I and minus 2. I see an e to the t, and then e to the it, so cosine t plus I sine of t. I can then put this all into the same vector to get an e to the t times a 1 minus I times a cosine of t plus an I sine of t, and negative 2 e to the t cosine of t plus I sine of t. Now I want to expand out this top term here, e to the t times cosine of t minus I cosine of t plus I sine of t, and then I have minus I squared, so a plus sine of t, negative 2 e to the t, cosine of t, plus I sine of t, and now I want to split this into real and imaginary parts. So I want to write this now as some vector containing all the real parts plus I times the vector containing all the imaginary parts. The bottom part's easy. The real part is just minus 2 e to the t cosine of t on this side, and then minus 2 e to the t sine of t on this side. For the top, I have two terms in each part. So for the real parts, I'm grabbing the two that don't have i's, so this cosine and this sine, to give me an e to the t cosine of t plus an e to the t sine of t. And for the imaginary, I'm grabbing the two that do have i's, so this sine and this negative cosine. So e to the t sine of t minus e to the t cosine of t. And that's my solution. So what the theorem then says is these two now separately are both solutions, and based on how they're built, they will be linearly independent. Which means my general solution is then C1 times the first solution plus C2 times the second one. So that illustrates the method and process for finding a complex valued solution to a system of equations, and then converting it into a real valued solution to that same differential equation system using Euler's formula to do so.